del cross del cross. So omega is this vector. Okay, so let us call it some minus e hat 3 omega scalar. There's no vector sign below it, times h3. So if I define it like this, then del cross omega, this will have the same stuff. Instead of psi, we will have this scalar omega. Okay, notice this h3, because when we had defined this, this was the scalar divided by h3. So I want to cancel that. Okay, I want to cancel that. So if I define my this function as e hat 3 omega h3, then del cross omega is something that I can simplify, and that will come out to be minus of h1 h2. So e hat 3 is there, minus of h1 h2 del by del c1 uh, h1 h3 over h2 del omega over del c1 plus del by del c2 h2 h3 over h1 del omega over del c2. And now this omega we know is defined like this. So this omega is defined as h1 h2 over h3 del by del c1 h1 h3 over h2 del psi by del c1 plus del by del c2 h2 h3 over h1 del psi over del c2. Okay, so what is this? This is basically, by definition of this E2 operator, okay, ignore this minus sign. By definition of this E2 operator, this is E2 of psi by H3, right? By definition of this E2 operator, this is E2 by E2 psi by H3. And what is this? Actually, instead of defining E2 like this, we should define E2 by this. There should be an H3 here, so that here I simply get an E2 psi. Okay, and what is the top? In the top, what is it written? This is nothing but E2 of omega. So there is no division by H3 here. So this is H3 times E2 of omega, and E2 of omega means E2 of psi. I just said that, okay, this is some omega times H3 times E hat 3. I just I have defined this guy here. So I am defining using this. Okay, I'm just, instead of writing the whole cumbersome expression, I'm encapsulating it in a simpler scalar variable omega. Okay, and so what is del square omega? What is del square omega for these flows? It is 0. So del cross of del cross omega, it is 0. Del cross of del cross omega is 0. So the governing equation for Stokes flows, for these Stokes flows, for flows which are 2D or axisymmetric, then the governing equation comes out to be E2 of E2 of psi is 0. The reason why I have defined a new E2 operator is because it is slightly different from del square operator. This is not your Laplacian. This is not your Laplacian operator. It is slightly different from your Laplacian operator, and you can go back and check how does this compare to Laplacian for a spherical coordinates. In cylindrical or Cartesian coordinates, you won't see any difference. Okay, because So let us take the example of h1 equals h2 equals h3 equals 1, and c1 is x and c2 is y. Once you take that example, so all of these h guys are 1. So del cross a, uh, del cross a simply comes out to be minus of k cap del square psi by del x1 or del x square plus del square psi over del y square, which is nothing but the Laplacian of psi. Okay, and then del cross, so this is omega, so this is equal to, again h3 is 1, so this is nothing but minus omega, this is nothing but minus omega k cap. So omega is del square psi. We know that del square of omega should be 0, which means del square of this scalar omega should be 0, which means del square of del square psi equals 0. In 2D planar coordinates, this E2 of psi actually reverts back to del square of psi. And just like this equation is called a harmonic equation or Laplacian equation. There's another word for Laplacian equation, that is, it's a harmonic equation. This is called a biharmonic equation. Let us take the example of cylindrical coordinates. So, in cylindrical coordinates, your C1 is r, your C2 is theta, H1 is 1, and H2 will be 1 by r. Okay. So, substitute that here, see what you get. So, when you substitute that in del cross A, so H1 is 1, so it will be minus k cap again. So, H2 is 1 by r minus k cap by r, del by del r. So, in here in cylindrical coordinates this is z, so h3 will also be 1. So, h3 is 1, h1 is 1, h2 is 1 by r. So, this is del by del r, r del c del psi over del r plus del by del theta, h2 is 1 by r, 1 by r del psi by del theta. Okay, and this is basically minus k cap. So, you can bring this outside. So, this is 1 by r del by del r del psi by del r plus 1 by r square del 2 psi over del theta square, which is indeed minus k cap del square of psi. Okay. So, the double cross product here as well gives you a minus k cap del square psi in the in the strictest definition, and from here you get del cross omega will be simply del square psi equals 0. So, the important point here is that del cross of anything will always give you del square, but why is it becoming e square, which is slightly different from del square in some more complicated complicated coordinates? The reason is that if you notice this here, so omega is defined as del cross a, which is the third component of this vector. Okay, which is the third component of this vector. So, you can go back and confirm that if I write any vector, let us say, then del square of a3 may or may not be equal to del square of a and its third component. That is the reason why we are getting different formulation of del cross omega when we are looking at a particular component. Okay, whenever you have coordinate vectors or the basis vectors to be specific varying with the coordinates, so e1 e2 e3 when they are going to be varying with the coordinates, then this is not necessarily going to be true, because when you differentiate del square a, when you differentiate this vector, you will have to differentiate the e1 e2 e3 as well. Okay, so this is not necessarily going to be true, and that is why we had to define this e2 operator. Okay, now in the spherical coordinates, in the spherical coordinates, the definition goes something like this. So you have this e2 operator. I'll just give the definition of this in spherical coordinates. This will be del 2 by del r square plus sine theta over r square. So you don't need to know how to exactly derive it, but I've given you all the tools so you can derive it from here. Basically in spherical coordinates, so this is spherical, h1 is 1, h2 is 1 by r, and h3 is actually 1 by r sine theta. Okay, and your c1 is r, c2 is theta, and c3 is your azimuthal angle phi. So whenever we have axisymmetric flows, so in spherical axisymmetric flows, it means that del by del phi is 0 in spherical coordinates. There won't be any variation in the phi direction. We can also look at the velocity components in the spherical coordinates from our definitions. So we had said that A is, let us say, E hat 3 psi h3. So h3 here is 1 by r sine theta. So here it will be E hat phi psi by r sine theta. And then del cross A, which is how we define the velocity, is, so E hat 1 h2 h3 del psi over del c2 minus E hat 2 h1 h3 del by del psi 1 of c1 of psi. So substituting your h1 h2 h3 here, we get E hat r, h2 is 1 by r, h3 is 1 by r sine theta. So 1 by r square sine theta del psi over del theta minus E hat theta, h1 is 1, h3 is 1 by r sine theta. So by r sine theta del psi over del r. So that means you have a radial component of velocity, which is 1 by r square sine theta del psi over del theta, and you have a tangential component of velocity, which is del psi over del r, 1 by r sine theta. Any questions so far? Please ask if there are any questions so far, because we are going to use this to solve for Stokes flow past a sphere. So now we are going to use this to solve for Stokes flow past a sphere. So let us say there is a sphere. Okay, I'm just making this ring so that you know this is a sphere, not a cylinder. And there is a flow, uniform flow of speed u naught that is that is going past this sphere. Okay, let the sphere have a radius of capital R. Or yeah, okay, let the sphere have a radius of capital R, and we want to solve for the flow past a sphere. Technically, we are always interested whenever we are looking at flow past some bodies. What are we interested in? We are interested in the drag force due to the flow past a sphere. Okay, the practical quantity of interest is the force on the sphere. Okay, not necessarily what are the velocity components at r and theta and different points. The usual practical quantity of interest is the drag force on the sphere, and that is what we will try to evaluate now. So before we try to do that, we know that the stream function psi satisfies this equation, that E2 of psi equals 0. What order equation is this? What is the order of this equation? E2 is what order operator? It's a second order operator, right? So E2 of psi will be what order equation? Fourth order. How many boundary conditions are we expecting? 4 in each direction. So second order, both r and theta. So we are expecting 4 boundary conditions in each direction. What are the boundary conditions on psi? How do we translate boundary conditions on psi? We can predict what are the boundary conditions on velocity. For example, we know that ur at r equals capital R for any theta is going to be 0. Why? This is a hard wall. Okay, the spherical wall is a hard wall. We are not entertaining any porosity of the spherical surface. There is no normal velocity on the inside or outside from the sphere. So ur is this. What does this mean? This means del psi over del theta for small r equals capital R is 0. Additionally, we know that u theta will also be 0. Why? U theta is 0 at the spherical surface. Why? Why is u theta 0 at spherical surface? No slip, right? This is simply no slip. So this means del psi by del r at small r equals capital R is 0. Okay. Now there is an important point here. Usually, I mean, although from JE cleared students this is not expected, but usually what happens is that students say, oh, del psi by del r at r equals capital R is 0. So psi is 0, or psi is a function of theta only. Okay. But if you say psi is a function of theta, does that hold at any r value or only at small r equals capital R? Right? You have to be very careful with this, that if you get a derivative at a point, you cannot comment about the value of the function at that point. Just knowing the derivative of a function at a point doesn't say anything about the value of the function at that point. Okay, so the only thing you can say is that psi is f of theta at small r equals capital R. And what can we say about this f of theta? We know that this guy is also the derivative of psi at this is 0, which means f is constant, which means psi is constant, which means psi is constant at r equals capital R. Now, does this value of constant matter to us? Does this value of constant matter to the kinematics of the flow? Does the value of psi being constant, does that constant value matter to us? No. Whatever that constant value you have, you're going to end up with zero velocity. Okay. So the absolute value of psi is of practically no relevance to us, just like the absolute value of pressure is of practically no relevance to us. Because in the Navier-Stokes equations, you'd never see pressure appearing. You have a gradient of pressure. So we can always add any constant value to pressure and still the Navier-Stokes, we can maintain the same flow. Basically, I can have the same flow here. I can have the same flow at 30,000, 3,000 meters above sea level or below sea level. Doesn't matter. Same thing happens with psi. I can add any arbitrary constant to psi and kinematics won't change. The flow will not change. So that means we can arbitrarily fix it to 0. Now, if you have a sphere of radius r, what can you say about very far away from the sphere? To be exact, what can we say when small r by capital R is much, much greater than 1? What can we say about when small r is much, much greater than capital R? That is, we are very far away from the sphere compared to its radius. Okay. Let us say radius is 1 centimeter. I am talking about 10 meters far away from the sphere. The flow will not see the sphere essentially, right? The flow will not see the sphere essentially. Now there is a very subtle problem with this, but we will come to that later. The flow doesn't see the sphere. That is not strictly true, but we'll come to that later. Okay. For now, we will assume that the flow doesn't see the sphere and u is actually equal to this u naught, let us say I cap. Okay. And now I want to write this I cap in terms of E hat r and E hat theta. So that will be simply u naught. So theta is this guy. Okay. Theta is this guy. So this is E hat r and this is your E hat theta. So what is I cap in terms of E hat r and E hat theta? Is simply E hat r cos theta minus u naught E hat r, sorry, E hat theta sin theta. Okay. So that means for r tends to infinity, we are saying that the radial velocity is simply u naught cos theta and the tangential velocity is minus u naught sin theta. So now when r is tending to infinity, I am saying this. So that means if I look at u r is 1 by r square sin theta del psi by del theta, which is I am saying is u naught cos theta. What does this mean? So all of this is happening at r tends to infinity. So I can take this r square sin theta d theta here and I can say that psi is some function of r. It's a different function from here. So maybe let me write g here. Some function of r times sine square theta, where this g of r is tending to r square or u naught r square for r tends to infinity. Actually, there will be u naught r square by 2, right? Because you have cos theta and then you'll have cos theta sin theta d theta. So if you assume cos theta to be t, actually this should be minus of gr, because there is a cos theta sin theta d theta. So cos theta derivative is minus sin theta d theta. So it will be minus gr. Just a second. No, no, there won't be minus because I'm writing sine square theta. So I'm saying sine theta is t, so cos theta d theta is dt. Yeah, you're right. So there won't be any minus. So this is fine. So this is what I'm saying, that psi is varying with theta like this. So an important conclusion from this that has happened is, when r tends to infinity, we got this variation of del psi by del theta. Notice I did not use u theta. I did not use del psi by del r. Again, because of the same thing. I cannot take the limit of the derivative and then integrate with dr. I cannot do that. Okay, I can do this. I can take the limit of r but integrate with respect to theta. I'm not at theta tends to some value. I'm still varying with any theta. I'm still having theta as any variation. Okay, so I can say that psi varies as this g of r sine square theta, where g of r is u naught r square by 2. Okay, and this gives us a variable separation guess. Okay, this gives us a variable separation guess that to solve this equation e2 of psi equals 0, I can take this g of r sine square theta and solve it. So let us calculate what will be e2 of psi when psi is g of r sine square theta. So let us look at that. So it will be g double prime times sine square theta plus sine theta over r square del by del theta 1 by sine theta. So g I can take outside because there is only differentiation with respect to theta. So sine square derivative is 2 sine theta cos theta. Sine theta cancels out. So what are you left with? G double prime sine square theta plus, what do we get here? Minus 2 g by r square sine square theta. Okay. So this again you can look at it as some h of r sine square theta, which means E2 of E2 psi will give us h double prime minus 2h over r square sine square theta, and this guy has to be 0. Okay. So what is h double prime going to be? So h double prime is going to be, so let us calculate h prime. H prime is simply g triple prime minus 2g prime over r square and then plus 4g over r cube, right? And then h double prime is simply fourth derivative of g minus 2g double prime over r square plus 4g prime over r to the power 4 r cube plus 4g prime over r cube minus 12g over r to the power 4. So this whole I can multiply with r to the power 4. So I will have 1 by r to the power 4 if I bring common. So this minus 2r square g double prime plus 8r g prime minus 12g. So we have this as h double prime, and then h double prime minus 2h over r square will give me this. So maybe let's write it here only. Will be minus 2h over r square. So minus 2g double prime by r square plus 4g over r to the power 4. What do we get eventually? We will get an equation that g fourth derivative minus 4g double prime over r square plus 8g prime over r cube minus 8g over r to the power 4. That is what h double prime minus 2h by r square gives us. The reason why I'm expanding this whole thing is because this looks like an equation that we know. Why do we know these kind of equations? Because if you look at it closely, then the powers of r, okay, dimensions of r are conserved throughout. This is the Euler-Cauchy equation. These kind of equations have a solution where you can simply assume g of r to be r to the power n and solve for possible values of n. Okay, these kind of equations have a polynomial solution. And this is linear. So this is, of course, powers of r are conserved and everything, but this is linear also. Okay, don't try to use this in non-linear and complain that, oh, I'm not getting any solution. So if I put g of r as r to the power n, then h becomes what? What is h? It is g double prime minus 2g by r square. So it is n into n minus 1 minus 2 r to the power n minus 2, right? That is what h is. So you will get, so now you have n minus 2. So we will have n into n minus 1 minus 2. So I'm writing h double prime minus 2h over r, what it will be. So then we have to treat r to the power n minus 2 as the function, and then we'll get n minus 2 into n minus 3 minus 2 again. Okay, and this you can open it up. This will be n square minus n minus 2, and this is n square minus 5n plus 4 equals 0. So this we can write as what? How can we write this? N minus 1, we can write this as, what are the factors of this? Hmm? N plus 1 into n minus 2, right? What are the factors of this? So this means my g of r can be some a, so n equals minus 1. So some a by r, n equals 2 plus b r square plus some CR plus some dr to the power 4. These are the possible, this is the linear combination of all possible values of n, okay, with all possible values of n here. Again, I can do this linear combination because it's a linear equation, okay. And now we try to use the boundary conditions that we had derived, okay. We try to use the boundary conditions that we had derived or whatever we had for psi. So first we will try to use this r tends to infinity equation, okay. So at r tends to infinity, this term will be 0, okay. This term will be 0. Which one dominates from all of these three terms? R to the power 4. And do we have any r to the power 4 variation in g of r for r tends to infinity? No. We know that r tends to infinity, g of r tends to u naught r square by 2, which means d is 0 and c is equal to u naught by 2. Oh no, sorry, b equals u naught by 2, because b is the coefficient of r square. br square is dominating cr, so I cannot say anything about c and a, okay. A and c are still remaining to be found. So from here we get that g of r should be a by r plus cr plus u naught r square by 2. I don't want to rub this part. We'll try to work here. Okay, so we know psi is going to be 0. Technically, del psi by del r at r, this is 0. Okay, del psi by del r at small r equals capital R is 0. So that means g prime at capital R is 0. Uh, let me write like this. So del psi by del r, this is the no slip condition. This means g prime at capital R is 0. So what do we get for g prime? Minus a over capital R square plus c plus u naught r by 2 is 0. You're right. Yeah, we need to know. We have to solve for both a and c. So basically, both the derivative of psi and the value of psi are 0 at small r equals capital R. So we'll use that. This is one equation, and the other equation is, so psi is 0. This means g of capital R is also 0, which means a by r plus cr plus u naught r square by 2 is 0. Okay, so we have to use these two to solve. Let me get rid of this part. So we have minus a by r square plus c plus u naught r equals 0, a by r plus cr plus u naught r square by 2 equals 0. So I can solve for c here, right? I can multiply this with r and I can add them. These guys will cancel out. We will have 2cr plus 3 u naught r square by 2 equals 0, which means c is minus 3 u naught r by 4. And so what do we get for a? So minus 3 u naught r by 4 plus u naught r gives you u naught r by 4. So a by r square is u naught r by 4. So we get a is No, no, sorry. A is this guy. So we have found this G of R. So G of R is nothing but U naught R cube by 4 R plus minus 3 U naught R by 4 small r plus U naught R square by 2. And so we have found basically our psi r comma theta. So I can choose to write it by taking this U naught R square common outside. Okay, so U naught R square, and then this becomes capital R by 4 small r minus 3 R by 4 capital R. Sorry, this will be, yeah, U naught R square plus R square by 2 capital R square times sine square theta. So we have solved for the stream function of flow past a sphere. Once we have solved for the stream function, we can use these two expressions to solve for velocity. I can solve for velocity u r and u theta using the stream function. Okay. So now the question is, you can find u r and u theta, but we are still remaining with the practical problem at hand. I have to solve for the drag past this sphere. So to know the drag past this sphere, I need to calculate both the viscous stresses and the pressure on the spherical boundary. On the wall of the sphere, I need to calculate both the pressure and viscous stresses. It's not like I don't have to calculate pressure. Okay. So how will we calculate pressure? How will we calculate pressure? How will I solve for pressure? Let's say I have psi, I have solved for psi, I obtain u r and u theta. How will I calculate for pressure? Or the Stokes equation, right? This is low RE number, low RE flow. So we know grad P equals mu del square u. So we have to solve this viscous stresses term del square u, and then we'll have to solve for pressure using this equation. We'll have to integrate the pressure over the whole spherical surface. We'll have to integrate the viscous stresses over the whole spherical surface to calculate the drag. Okay. So look at Panton's, I think chapter, which one is it? Look at Panton's chapter 22, 21 and 22. Okay. We'll cover that on Tuesday, but I want you to understand, because after this, it's just integration of the forces. Okay. Integration of stresses. There's really no fluid mechanics particularly required. We have solved for velocity. That's it.